Let's bow our heads. Dear Heavenly Father, we thank you that you have given us such a beautiful day to come today and to worship and talk together. We pray a special blessing on our speaker, Dr. Kootsey. We pray that you will bless him as he presents the topic on intelligent design. We pray that you will be with us as we hear and as we discuss. And we thank you that we have this opportunity to worship in this open place of freedom. We ask this in Jesus' name. Amen.
Thank you, Judy. And with that, we're going to invite our speaker to come this direction. And I'm going to ask him a couple of questions, too, to find out more about him. And he's wired for sound up here, okay. Dr. Kootsey, according to my records, you've been receiving tapes from San Diego Forum since about 2002.
Yes, I think that's right.
How did you first hear about us?
Well, the first thing is that I've been a member of the Adventist forums in general for a very long time.
Okay.
Almost since it was organized in the Boston area. I was a graduate student in Providence at the time.
Okay.
And my wife and I would drive up to Boston to participate in the discussions there. This was in the 60s.
Okay.
To be honest with you, I can't tell you exactly how I heard about this one. It may have been an announcement in the Spectrum, or probably it was a friend in the Loma Linda area where I was working and teaching at that time.
Okay.
Because a number of my friends are either recipients of the tapes or do attend here.
Okay. Even in Loma Linda?
Even in Loma Linda.
Now, how did we become aware of your interest in being a presenter?
Actually, I contacted Elwin Dunn first and spoke to him about something I thought might be of interest to the group. And he said, well, I really needed to talk with you.
Okay.
So it got started that way.
And that led to today.
It did.
Now, in the newsletter, we have a very fascinating bio vita piece that you shared with us. All the different things you've done in life. Mm-hmm. I don't know if that meant you couldn't hold the job and had to move on or just what. But anyway, you've done a lot of things. But one of the things that got my attention, other than your background in nuclear physics, et cetera, and doing a new simulation program, is the class you taught in music. Mm-hmm. What was that, and to whom?
This was at Andrews University while I was there, and the class was actually in music technology, not mathematical, but keyboards, electronic keyboards, sound generation, the software programs for writing, publishing music, and generating accompaniments and that sort of thing.
Okay.
It was relatively unknown in the music department at that time, and I was a very good friend of the chair of the department. He was also a piano performance person, so that led to the teaching of this course for the students.
Well, that relieves my mind, because I couldn't figure out if you were a Bach person or a Beethoven person. Now I know you're just a technology person. Let's welcome Dr. Mailen Kootsey. Okay?
Thank you very much. Get the computer moved back over here. Being involved in higher education for 40 years, I could not resist starting my presentation today with a quiz. This is going to be a very short one, and to relieve your anxiety, it will not count on your final grade. So I would like you to give me the answer. This will be a one-question quiz, and here it is. We're looking down on the top of a cyclist approaching a corner. The cyclist is moving in the direction of the arrow that you see. When the cyclist gets to the corner, he or she would like to turn right. Now the question is this, one simple question, and I'll take hands in a moment. Which way should the cyclist turn the handlebars to make this right turn? Okay, I'll take, let's have a little vote here first. What about the people who think the cyclist should turn the handlebars to the right? Hands on that? Okay. I didn't count, but I'd say that's probably a majority. How about those who think the cyclist should turn to the left? Several. You're not in the majority, but at least 7 or 8 there. How about those who don't know? Good, some honest people here. Great. Okay, the answer is, ding, 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 left. You have to start turning left in order to turn right. Now let me see if I can give you a quick explanation of why that is the case. Let's look at this cyclist from the back first. Now this cyclist riding down the street is riding vertically. Of course, we hope so anyway. If the cyclist went to the corner and needed to turn right, what kind of force would that cyclist feel? Now you know what happens when you turn a corner in a car. If you're turning right, what kind of force do you feel as a passenger or driver in the car? You feel a force to the left, correct? Why is that? According to Newton's laws, your body wants to keep moving in the direction it was going, which was straight ahead, while the car is turning right. So this ends up as feeling a force to the left. Now, when you're riding in a car, you've got at least 4 wheels on the ground, so you can sustain a force to the left without being pushed over, without falling over, because the wheels can accept that sideways force. But when you're on a bicycle, you can't accept a sideways force like that. You'll fall right over because the wheel only touches the ground in one place and you're like a lever. You just pushed right on over it. So how can we turn right if that's the case? What we really need is to be leaning right to start with, so that that force that we feel, we give it a name of centrifugal force, which is actually a fictitious force, but we can call it that. That force that we feel pushing to the left will balance by leaning to the right. Okay? So that if we do that just right, it will be balanced and we can maintain our equilibrium as we go around the corner. Now the question is, how do we get started leaning right? Well, to do that, we attempt to make a turn to the left. Because if we attempt to make a turn to the left, that centrifugal force will naturally push us over to the right, just the direction that we need to be going to make the right turn. Now you might wonder, what does this all have to do with intelligent design? I'm going to let that lay for a little while, and we'll come back to that in a few minutes. But I hope you get the idea here that although you probably have a decent understanding in your mind, at least an intuitive feel for the laws of motion, for example, that if you're moving in a straight line, your body or the car or whatever tends to continue in a straight line, and the other related laws of motion. But there's a difference between knowing what the laws are and the behavior resulting from those laws. And that's something I'd like to work on a little bit later in the talk. The difference between knowing the laws and the resulting behavior. So let's get into the design issue. Probably the most famous statement about intelligent design comes from William Paley, written about 1802. And I have a slightly abbreviated version of it here that we can read together. I'm sure you've seen or heard this before somewhere along the line. In crossing a heath, suppose I pitched my foot against a stone and were asked how the stone came to be there. I might possibly answer that for anything I knew to the contrary, it had lain there forever. But supposing I had found a watch upon the ground, and it should be inquired how the watch happened to be in that place, I should hardly think of the answer I had before given, that for anything I knew, the watch had always been there. Yet, why should not this answer serve for the watch as well as for the stone? For this reason and for no other, namely, that when we come to inspect the watch, we perceive what we could not discover in the stone, that its several parts are framed and put together for a purpose. Now, William Paley did not originate the idea of intelligent design. He was definitely a well-known, well-written, well-respected philosopher and theologian. In fact, his books were still used as the basis for examination questions right up to the beginning of World War I. We can trace some of the ideas in intelligent design back to Plato, writing to the voice of Socrates. At the death of Socrates, Socrates himself was calm and said that he was not fearful because either, he expected, there would be a pleasant place, a thought that would follow, or there would be a God who was loving and would take care of him, whichever way it went, or even if that death brought him to a dreamless sleep, he would be happy. And he concluded, as part of the argument, he knew about that God, or felt that he did, because the artifacts that he was familiar with could not come into being through blind chance. Therefore, there must have been a designer. That's Plato's argument. Years later, Aristotle also made an argument. His theme was the final cause. He didn't speak directly toward design, but talked about a final cause, a purpose for each object and individual. Many years later, Augustine also wrote about final causes in his writing The City of God. Still later, St. Thomas Aquinas gave that same cause as one of the 5 proofs for the existence of God. So this general idea of purpose and design has been around for a long time. These people thought about it in slightly different ways than we do today with our scientific background, but nevertheless the idea of a designer has been there. Now we can move up to more recent centuries. We've already mentioned William Paley and quoted from him. In addition, in the 19th century, George Cuvier, well known for his original work in the area of comparative anatomy, stressed the complexity that he found in biological systems. And again, like his predecessors that we mentioned here, talked about final causes. Charles Darwin, in a list of intelligent design, well, Charles Darwin was a religious man early in his life, and even as he wrote about his ideas of evolution, he used terms such as selecting, preferring, seeking only the good of the species, words that we could say would be anthropomorphic. And his competitor, friend but also competitor, Wallace, with whom he had long exchanges of letters, accused him of really having in mind a designer behind his processes. So that this discussion went on through a whole series of letters. Even though the idea of intelligent design has been around for a long time, something different has happened in the last couple of decades. To show the difference, in my presentation here today, I'm using capital letters to refer to this recent movement, intelligent design ID capitalized. This movement really started with a book by Michael Denton, Evolution, A Theory in Crisis. Now, Denton was not the originator of the ideas that he wrote. He was not one that started a criticism of evolution, but he was a compiler of ideas and data from a variety of different sources. And you see his book was published 1985, in Europe, 1986 in the United States. He didn't talk about intelligent design or anything like that, but this was a kind of seed that started the recent intelligent design movement. Philip Johnson was a member of the law faculty at University of California, Berkeley, and in 1987 he went to London for a year's sabbatical. The first couple of weeks that he was there, he had not selected a topic that he was going to study during his sabbatical. And he wandered around among a number of subjects trying to find something that would be interesting to research during his sabbatical year. One morning, he made his usual walk from where he was living to his office, a matter of a few blocks, and he passed by a large bookstore and noticed in the window of that bookstore a display of two books. One was the book by Dawkins, The Blind Watchmaker, and the other was Michael Denton's book. He was curious about the two. He saw immediately, even from the titles, that they were on opposite sides of an argument. So he went inside, paged through them a few moments, and was intrigued. As a trial attorney, to find a subject where there were two sides that could be argued, this caught his attention. He bought those two books, took them to his office, and didn't stop reading till he had read the two books through. He decided immediately that this was a subject that he would work on during his sabbatical. He began writing almost immediately, and he also started reading. He was not educated in evolutionary biology or any of the related subjects, but he began reading voraciously immediately for the next 10 months while he was on his sabbatical. And before he left England, before he left London, he had produced a paper entitled Science and Scientific Naturalism in the Evolution Controversy. When he got back to Berkeley in 1988, he sent out copies of this paper to many of his friends and colleagues on the Berkeley campus and called together a faculty seminar on the subject where he could present his paper and get critiques from his colleagues. This was really the beginning of the recent intelligent design movement. Johnson got an attendance of about 20 people, give or take a little, at his seminar. Not as many as he had originally hoped, but there were several evolutionary biologists that came to that meeting and about 4 or 5 faculty from his own department. So they were key people that helped him crystallize his ideas. He went on then to write the book that really initiated the intelligent design movement, Darwin on Trial, and that was published in 1991. Now, other names that are well known in the recent intelligent design movement are Michael Behe and William Dembski. Michael Behe is a chemist, and he's the one who originated the idea, well known in the intelligent design movement, of irreducible complexity. I won't go through the arguments for that today, but I'm sure many of you have seen that argument before. It was, in fact, based on a statement of Darwin that said, if we could find a system in the biological world that could not be produced by a series of gradual changes, then his theory would fail. And Michael Behe built the idea of irreducible complexity on that concept. His first book on the subject was Darwin's Black Box, 1996, and has published several since then. The next person to get on board was William Dembski, a student in the early 90s. He was a mathematician, And his claim to fame in the intelligent design movement is the construction of an ideological filter to recognize design. The filter looks something like this, a series of steps, and again, I won't go through this in detail today. Any event or series of data, observations, would have to be passed through this filter and arrive at the bottom in order to be considered design. Has to match to answer to three criteria: contingency, complexity, and specification. And to simplify this in just a brief statement, what he is looking at here is the probability, primarily, of the likelihood of a given event or set of data being produced by a chance mechanism. Now, the idea is that if that data passes through this filter, then it is evidence of design. Now the question is, what does one conclude from that? Primarily, the intelligent design movement has based its concept on these two steps. One, the event or observation must pass the design filter. Second, if it is design, then it could not have come about through a chance process, such as evolution, and it must have come from an intelligent designer. Now, I'll have a little bit more to say later about whether that means God or a person or what, but we'll come back to that. I'd now like to pause for a moment on the intelligent design issue and talk about what it means to prove something in the scientific community. I'm going to describe three different kinds of proofs, and then we'll come back to the intelligent design two-step process and see where those steps fit into these types of proofs. The first one is proof in a closed system. Now, a closed system means that there's a finite amount of data that has to be accounted for. It might be a large number, like 1 million, but at least it doesn't go on forever. You've collected the data and you're done, and that's all there is available. Now, most of the closed systems that scientific and mathematical people are interested in are, in fact, mathematical systems, human constructed. Not data from the real world, but data from hypothetical systems, human constructed. And so I've shown the flow of logic here. We start with premises that are assumptions about this system. We have some rules of logic that we can use to combine those premises. And then the task is, can we take any statement about those data items and see whether or not they're consistent with the premises? Can we prove that they are or not, that statement is or is not consistent with the premises according to the rules of logic? Now, I've given you an example down below from Boolean algebra. Clearly a closed system. Talking here about a system with just two Boolean variables. Each of them, A and B, can take on the values false or true. So on the left-hand side, we have a statement. The operators in Boolean algebra include or, not, and there's some others too, but we'll just think about those three. So I have a statement here that says A ORed together with B is equal to not A and B. Now that's a statement. That's an equality that we can test. In order to test it, since there's only 4 combinations that A and B can have, we can test all 4 combinations and prove that statement absolutely true or false. And so you see the proof on the right-hand side, the 4 combinations of false and true for A and B. False, 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 true, and so on. And we can test what the values of each side of the statement would be for each of those combinations. They match up, so we have a formal and final and absolute proof that that statement is true in the Boolean algebra limited world. Now, there are other closed systems besides Boolean algebra, of course, but that's an easy one to show very quickly. The second type of proof I'd like to talk about is proof in an open system. Now, here we have an intrepid scientist with his binoculars recording data on a strip of paper as it comes out of the machine. And this magic machine is at the same time generating a mathematical model of this data that comes out on a different strip. Now, unfortunately, this scientist is cheating a little bit. If you look carefully, you can see at one point his data didn't match his model, and so he canceled it out and wrote in the correct value according to his model. So no real scientist would do that, of course. What this illustrates is the process of collecting data, thinking about it, trying to find the patterns in it, and coming up with a description of that pattern, whether it's verbal or ultimately maybe mathematical in nature. By an open system, I mean this is now data observed from the natural world, so there is never an end to that data. No matter how long you've been measuring it, how many points you've collected, you can always do some more tomorrow, next week, and next year, and maybe even better if you can get better instrumentation in the future. So when we're making measurements and recording data from the real world that we live in, that is in fact an open system where there's always more data. Now, what does proof amount to in such an open system? Well, our objective in the open system is to find this law or regularity or pattern. We would call success in such a world if we could find a law or pattern or mathematical relationship that was highly successful in predicting the data. And scientists have a number of ways of going about doing this. Generating a new experiment to try to test their hypothesis, collecting more data, trying hard to break the hypothesis. That is, trying very hard to find examples that would not conform to the hypothesis, and so on. I won't go into all of that now, but success means finding a hypothesis or ultimately a law, if we have enough confidence in it, that represents the data from the real world. Is it absolute? Certainly not. It's the best we can do with the data that we have and the creativity that we have in our minds for thinking through that data and finding patterns in it. But it is by no means absolute. It is always tentative in some sense. Even something as well established as gravity still has a certain amount of tentativeness to it, and people continue to make measurements based on known laws. The illustration here is from a 1660s woodcut, and it is a perpetual motion machine. You can see there that tray about 2/3 of the way up is full of water. The water comes out a little spout on the left-hand side, falls on the water wheel, turns the water wheel through a series of gears. There is a spiral water lifter pump that carries the water from below back up to the tray again. And the hope was that since this is a cyclic thing, that this would run forever. Now, of course, we know, and I'm sure they found out if they tried to build this, that that didn't happen at all, because there's something else going on here in addition to the moving of the water. There's friction. And we now know that according to one of the best laws that we know of that has come out of the second type of proof that I talked about, conservation of energy, is that this is basically an energy-losing machine. Whatever you put in to start with, it will gradually disappear through friction and heat in the gears and the bearings of this system. So it might run for a brief period of time, but it's going to stop pretty soon, and it's definitely not a perpetual motion machine. So this is a conclusion based on a known and pretty well established law, that is conservation of energy. How certain is this conclusion? Well, I guess it's pretty obvious that it depends, first of all, on having a law, a trustworthy law that you're basing it on, or combination of laws to start with, so it depends on that. Second, it depends on how carefully we have analyzed and applied those laws. For example, our forgetting of friction means that our conclusion is incorrect because we've left out a factor that is important in this machine. So, type 3 proofs are variable depending on the reliability of the laws applied, depending on the skill of the person building the conclusion on those laws, and whether or not they have successfully taken into account all the factors that are important. Now let's come back to intelligent design, our two-step process. I'm not going to say any more about the filter now. To discuss that really is quite a technical issue. So let's look at the second step here. If it is design, then it could not have come about through a chance, natural process, such as evolution, and it must have come from an intelligent designer. What kind of proof is this, according to the three that I have outlined for you here? Is it the first type, a closed system? No, clearly not. This is measurements from the natural world, so it's not a closed system. 2, is it from the second type, that is, an open system? Well, yes, we're certainly talking about an open system, but the point here is not necessarily to develop a new natural law, but to come to a conclusion, really, based on known natural laws of probability and others. So I would say, you might have your own opinion of this, I would say it's really of the third type that I talked about. That is a conclusion based on existing laws rather than trying to come up with a brand new one. Now, how good and solid is that conclusion? Well, the laws of probability are certainly well known and well studied mathematically, so we don't have a weakness on that point. What about the other part of the argument here? Does this argument take into account all possible processes and factors? We now know that there's something missing in this argument, and let's move on to the next part of my presentation. This is a conclusion based on known laws, and does this imply, if it was true, does it imply the supernatural or not? I'll say a little bit more about that later as well. Next, I'd like to show you a little bit of mathematics. It won't depend on your knowledge of mathematics, but I'd like to give you a couple of ideas that I think are important from mathematics. Let's think about, first, an object falling under the influence of gravity. It turns out that all the natural laws that people have come up with, scientists have come up with, really are laws about relationships. I won't enumerate that, but just to give you one example, the law of gravity says that if there are a couple of bodies in the universe that have mass, they exert a force on each other. That is a relationship kind of law. So this object falling under the influence of gravity, if we're going to describe its behavior, if we want to understand what it does, we start out with those relationships. And the relationships that we need here are, in fact, gravity, the force felt pulling the apple to the earth and the earth to the apple. And if we want to think about the motion of that apple, we have to include Newton's second law of motion that relates force and acceleration. Those are both relationships. If we combine those relationships, we get another equation that you see here. That is a relationship type equation. Unless you're a skilled mathematician, you can't look at that equation and tell anything about what that apple is actually going to do if you hold it up above the ground and let it go. In mathematical terms, what it means is that we have to solve that equation because it's only a relationship equation. So the equation at the bottom is, in fact, the general solution for that relationship equation. And that the bottom equation describes the behavior of that apple. It says that given a time that the apple has fallen, we can, and where we started, how high the apple was when we let it go, we can tell at any given time where the apple is going to be, according to this equation. And what is important about this example is, number one, that we started with relationships and ended up with a description of behavior, but also this description of behavior is general and complete. It doesn't matter how big the apple is, what kind it is. In fact, it can be a ball of lead, if you like, or a book, or an automobile, or a grand piano, or anything else. If it's going to fall to the earth, it will behave according to that equation at the bottom. Now, we have made some assumptions here, left out the friction of the air and a few other things, but to a reasonable approximation, that equation describes behavior of any object under any conditions, as long as we know the starting height and the gravitational constant for whatever planet that apple is being dropped on. Now let's look at another gravity type problem, the three-body problem. Now, rather than one apple, one earth, we have three bodies. It could be apple and a pear and the earth, or whatever you like, three planets or anything else. Each of those exerts, according to the law of gravity, a force on the other two. So we have this mutual force relationship. We start out again by looking at those relationships. We have the gravitational attractions and the Newton's laws of motion again. I didn't put the equations this time, but we could write those down. Now the question is, what is the behavior? And I put question marks here because this particular problem does not have a general mathematical solution. That is, I cannot write one equation down here that describes the behavior of those three bodies under all circumstances, like we could in the other case. The only way we can make use of that relationship equation is to start with a known distance between these three objects and their motion at the starting time, and then by following through the equation, watch what happens. Literally making the equation go step by step to follow the behavior of those three objects. Now the difference is, if we do that, we have only solved that problem for the one case of that particular starting set of positions and speeds or whatever other motion they have individually. All you have to do is change the position a little bit, and we have to start all over again to find a different solution. So I've shown you examples here of two kinds of mathematical problems. One where you get a general solution, you know what the answers are in all cases. The other kind where you can only get one at a time, and there may be an infinite number of them. Now the question is, which occurs most often in the real world and real science? 99.999, you name it, % of the equations that are useful in the world are of the second type. That is, no general solution. Now, I was a physics major, and we studied lots of equations, not only of motion, but electricity and other things. And the people who wrote the physics textbooks were very clever, and they found simple problems that we could find closed solutions and general solutions to in many cases. But we had certainly learned when we got out of school, if we didn't know already, that those were very special problems and didn't match the real world very often at all. So the real world problems, certainly in physics, and even more so in chemistry, and even more so in biology and other sciences, are really mostly of this second type, that you do not get a general solution. You have to take specific cases and step it through one step at a time. Now, this is only a three-body problem. What about our cyclist here? Didn't we have the same kind of thing there? We knew what the relationships were, but we didn't know what the behavior was. And our intuition is not to be trusted in this area. Many of you had the intuition from riding tricycles and motor vehicles that you should turn the wheel to the right, but it turned out to be wrong. And so intuition is not very trustworthy in terms of guessing what the behavior is from looking at equations. Here's an example from my own field of interest. A description generated in the late 1940s, published in 1952, won the Nobel Prize. It's a description of the electrical activity of a little patch of cell membrane in a nerve cell. On the left-hand side, you see an electrical circuit that is used to summarize the behavior. This circuit is really derived from data taken in the 1940s. And the question here is, if we write the equations for that circuit, does it in fact mimic the behavior of that nerve cell? And so the scientists, by the names of Hodgkin and Huxley, in around 1949 or so, wanted to solve the equations on the right-hand side of the page. There were no laptop computers available in that day, of course. It so happened they were in England, and there was in a laboratory in England one experimental computer. So they went to the lab and said, "We have this very important problem in biology. Could you give us some time on your computer?" And they said, "Yes, we will do that." But before they could get started with it, the lab directors decided to tear this computer down and work on it. So the poor neuroscientists were very disappointed, and they said, "We can't wait 6 months, so we're going to do this by hand." And they did. They had a mechanical hand-cranked desk calculator to do the arithmetic for them, and they were able to find a solution in 3 months. They beat the computer by 3 months in this case. Of course, that wasn't the computer's fault. So finding solutions to a set of equations, even this is relatively simple by biological standards, is quite a significant piece of work, a significant computational job. Really only helped now by modern computers. I'd like to show you, oops, something has happened to our internet connection. Give me just a moment, if you will. think it shut off because I wasn't using it for a while. Okay, we're back again. All right, now we can go back to our presentation. And let's see if we can find our example. This is a reconstruction based on the same mathematical equations that Hodgkin and Huxley developed. The equations are behind the scenes, and you see here a little animation of the cell, and on the right-hand side, a graph like Hodgkin and Huxley would be looking for on their oscilloscope or in their calculated data. So if we start the calculation, this calculation is actually being done as you watch it now. This is not pre-calculated. Now remember, it took Hodgkin and Huxley 3 months to get that answer. Okay? And in this case, I've actually slowed it down for you so that you could see it develop. Otherwise, it would just pop up on the screen like that. So we've only really been able to make some headway in many of the equations that we are hinted at from the real world since the age of computers. The computation is simply too intense. And the whole point of this, as well as any other mathematical model, is to make a change in what happens and do it again. Here I'm changing the amplitude of the stimulus given to this nerve cell, and you see its behavior changes. Those are properties that come from those mathematical equations when we solve them. Now, in the last decade or two, there's come to be known a relatively new idea called emergence. And here I've given you 2 definitions of emergence. The first one is from that well-known, trustworthy source called the Wikipedia on the internet. Emergence refers to the way complex systems and patterns arise out of a multiplicity of relatively simple interactions. The second definition comes from a publication by Goldstein in 1999. Emergence is the arising of novel and coherent structures, patterns, and properties during the process of self-organization in complex systems. Now we'll have to explore that idea a little bit. What do we mean by self-organization? Now, for decades, hundreds of years, the primary method of science has been reductionism. That is, if you have a system that's too complex to understand, you try to break it down into simpler components that interact with each other. It's just a standard method. If you want to understand the circulation, you break it down into the heart and the vessels. If you want to understand the heart, you break it down into regions. If you want to understand those regions, you break it down into cells and so on. That seems to be a standard method, and we're interested in the interaction between those components. So that in itself, components and interactions are not new. That concept is not new. Emergence takes this another step beyond, because when you take a system apart, you're not necessarily learning anything about how it got that way, how the system got interconnected to start with. But emergence addresses the issue of where that complexity came from. And we're now finding that many complex systems built out of relatively simple components actually generate organization and complex behavior themselves without outside intervention. Now, I'd like to give you an example of that. This is again from the web, a website from MIT. And let me click the start button here so you can see what's going to happen, and then we'll talk about what it means. You see a little shape going across that black box. This looks like an object moving across the screen. In reality, it is not. In reality, what we have here is a black square that's really subdivided into a large number of small squares. Each of those small squares can be either white or black. And there's a set of rules built into this system and a clock that keeps advancing the time. And each time that clock makes another tick, those squares have to behave according to the rules. And the rules are very simple. They're shown here if you can read it. If a square is on, it turns off at the next step. If a square is off, it turns on if exactly 2 of its 8 neighboring squares are on. Pretty simple rules. Okay, I'll start this one up. You can see we now have several of these things. They can go right or they can go left, and they can go up. What do we have here? I didn't say anything about gliders, movement, or anything of the sort. The rules are well known and they're very simple. Squares turn on and they turn off, and that's it. We have something of interest and complexity and design maybe emerging out of this system without building it in. Nobody had a blueprint for this. It simply resulted from the internal laws that are there. We can go on here. Another page or two. Might get some response from the site. This one starts by saying gliders can come from very humble beginnings. Just 2 little squares to turn on. Same rules. Hit the start button. And now we not only get gliders, but gliders that multiply. And if we wait long enough, this turns into a real mess. Overpopulation, I guess you'd call it. You could go through the rest of this website. They change the rules a little bit and show you how changing the rules also changes the behavior. But the point I'd like to have you take away is we know exactly what the basis of this system is. We've generated the rules. It's man-made. It does only follows the rules that we put into it. Yet we get out of it something that we didn't expect, we didn't dream of. By reading those rules to you, could you have predicted what those things are going to do on the screen? I dare say not. I certainly couldn't have. This is an example of emergence, and we now know, once recognized, that there are many examples of this, more new ones being recognized in the natural world all the time. I've brought examples of just a few of them. Army ant raids. This shows a pattern of the raids. These army ants start in what's sometimes called a bivouac, a camp, so to speak, and they march out for food, and these are the patterns that they take, 2 different patterns according to the different availabilities of food. Now the question is, how is this pattern generated? Who directs the ants? Is there a general? Are there sergeants? A hierarchical organization? No, there's nothing. Each individual ant has a set of rules by which it follows. But somehow, because of the interaction between those ants, an organized behavior comes out of it. And people have now replicated this in the computer once again. Here you see the ant trying to make a decision of which of 3 squares to move to next. And it turns out that the correct laws here have to do with the ant's sensing of pheromones from its predecessors on the trail. And the location of the pheromones will alter the probability of the ant going one direction or another. It's really a very simple set of rules. And now you're looking at simulations of the army ant raiding, which follow along very closely with the observations. By the way, these army ant raids and the bivouacs and so on have been said to be the largest non-human biological congregation known on our world, of the order of 1 million army ants together, working together in this pattern. A second example, again from the insect world, these are termite mounds from Africa. These are termites that grow their own food. They grow fungi. And they build these mounds to hold and to ventilate their fungi farms. I won't be able to go into a lot of detail here, but Scott Turner, who has written a book on this and a number of other emergence areas, has been able to discover why the termite mound has the shape it does, why the mound is tilted in the direction that it is. Just give you a clue here. The tilting is because of the heating of the sun. If the mound was straight up, it would be warmer on one side than the other. Oops. Sorry. It would be warmer on one side than the other. And so the ants in their individual behavior, remember, there's no general, there's no queen telling them what to do here. Each one individually does its own little work and interacts with the other ants through pheromones and so on. But they move the dirt in such a way that the mound ends up pointing directly at the sun so that both sides get warmed identically. Scott Turner, in writing about this, said he finally realized that this termite mound is not a structure built for a purpose. It is actually a process, ongoing all the time. That is, rain and wind and weather wash away this mound, and there's a constant stream of soil being brought up from below by the ants, as much as 500 to 1,000 pounds a year being brought up grain by grain by the termites. So the mound is actually a living, breathing thing in a way. And the termites build this mound so that they have the correct temperature, the correct carbon dioxide concentration, and the correct humidity inside. It's a fascinating read if you can get Scott Turner's book. Talk about how he discovered this. Last example is from a book written by a friend of mine, actually, Dennis Noble from Oxford. Worked in the same area of cardiac electrophysiology that I did for many years, and we've been together at numerous meetings. He published this book about a year ago called The Music of Life, and that attracted my attention immediately because of my interest in music. The main theme of this book is very interesting. He talks about the genome and how it affects the body and the living things in general. And his conclusion is surprising.